middle, I believe, switched out. But the person here is like, meh. So. Hey, we're live. There we go. We got 3 people in the chat. I might have just broken your eardrums and your computers by saying you're live in such a loud September 21st. We're back on Monday. It's great. I'm back. I'm still kind of a little sick, probably like 95% better, something along those lines. Fun fact, my son had to get tested for COVID. Have you guys ever been tested for COVID? They stick a kind of a Q-tip type thing, like way up your nose. It sucks. Well, my son came back negative, which is great, because if he came back positive, then I probably wouldn't be here for a couple weeks. I don't even know. But I'd still be teaching. I'd still be doing my thing. And you'd still be learning, you people in cyberspace watching the live stream. So, as a reminder, I told everybody here in the classroom, for those of you in the chat, please make sure you realize that there is a quizzes that is due tomorrow. Please make sure you're jumping on top of that. I am going to be assigning you another assessment before the end of the week. Online textbook. I've been messaging people about online textbook. I am going to be assigning you stuff out of the online textbook as well. But we'll get there when we get there. I just need to make sure that you're jumping on that online textbook. Anyway, ladies and gentlemen, I want to start off today with a video. Now, this video is kind of corny, kind of whatever. For those of you that are in the chat, I'm going to try to have the microphone near the speaker so you're able to hear what's going on. But you can easily find this video on YouTube. Algebra 69 quadratic equations. You'll probably see it if you can, but I'm going to try and play it right here. I want everyone in this classroom to listen to what this man has to say in his cartoon voice, in his kind of whatever way. It's going to set up what we are going to be doing today, and I'm going to be giving a more detailed explanation when we get back to actual work. Here we go.
Hello, I'm Professor Von Schmohawk, and welcome.
I did not make this video.
So far, we have introduced quadratic functions and have seen that the graph of a quadratic function in a single variable is a parabola. If we set a quadratic function equal to 0, we produce a quadratic equation. Although quadratic functions and quadratic equations look similar, there are some important differences. For example, let's take the quadratic function x squared minus 4. Like all quadratic functions, the graph of this function is a parabola. Now, if we set this function equal to 0, we produce a quadratic equation. This equation has 2 solutions, x equals 2 and x equals -2. So although the graph of the function x squared minus 4 is a parabola, the solutions to the quadratic equation are the 2 points where the parabola intersects the x-axis, also known as its x-intercepts. These points are called the zeros of the function. In general, the zeros of a function are the input values that cause the function's output to have a value of 0. So for a function of x, the values of x which cause the function to produce a value of 0 are the zeros of the function. These zeros are sometimes called the roots of the function. Finding the zeros of a linear function is easy, since unless the function's graph is a horizontal line, it will always have a single x-intercept and thus a single 0. To find the zero of a linear function, we determine its x-intercept by setting the function equal to 0 and then solving the equation for x. On the other hand, a quadratic function of a real variable may have 2 x-intercepts, 1 x-intercept, or no x-intercepts. But solving a quadratic equation can be much more complicated than solving a linear equation.
I am going to skip a certain part of this video that I don't care for.
The problem of finding the solution to simple quadratic equations was encountered at least
There we go.
4,000
I'm going to
years
skip
ago.
this portion of the video because I don't want it. There we go. That's part
As
one.
an example, if a cannonball is fired from a cannon 12 meters above the ground, and the cannonball has an initial vertical velocity of 80 meters per second, then according to the laws of Newtonian mechanics, the height of the cannonball above the ground would be given by the function negative 5t squared plus 80t plus 12, where the constants in this quadratic expression are determined by the physical parameters of the example, and t is the time elapsed after the cannon is fired. If we wish to find the time it takes for the cannonball to hit the ground, we set this expression for the vertical height equal to 0, and solve the resulting quadratic equation for t. Solving this equation requires a mathematical technique more powerful than anything that the Babylonians or Egyptians had in their mathematical bag of tricks. In the next several lectures, we will explore techniques.
Yeah, I'm not going to have you walk through. I'm not going to have you walk through several lectures with this guy. I liked the visual. I liked what he was doing with that thing. Now let me flip the camera over here so you can kind of see what I'm going to do next. Let's see. F of t is equal to negative 5. I'm going to do x here. We'll do g. Yeah. G of x is equal to negative 5x squared plus 80x plus 12. Now, I'm going to zoom out just a little bit so you can kind of see what's going on here. Haha. Change this weird functioning screen here. Now, check this out. It's a little hard to see, so I'm trying to get the screen to be the precise size that I want. But there's a blue line that is represented by this function. And the idea is that this blue line, I'll put it in a little pink right here, is that there is a cannonball that is fired. And it goes up, and then it comes down. And it's something along the lines of, well, this cannonball was fired 12 feet off the ground. It follows a parabolic arc, and then it slams into the ground, simply destroying and eviscerating anybody in its path. And the question becomes, well, where will it hit the ground? Or how long will it be in the air? Those kinds of questions can be answered by solving these types of quadratic functions. Knowing precisely where that thing is going to hit the ground is the bread and butter of Algebra 2, one of the bread and butter of Algebra 2. It's one of the main things that we are going to learn in the first half of this school year, solving quadratic functions. And eventually, bear with me, eventually this is going to translate into your favorite type of math problem. What's your favorite type of math problem? Let me re-express that. What is your most hated type of math problem? What would you say? I already know the answer. I just want to know what you think. What type of math problem do you look at and just sends chills down your spine? Type of math problem that you look at and then you immediately like, nope, skip it, move on to the next one. Agree or disagree? Word problems. Yes, this is going to translate directly into word problems. I love it so very much. Now, let me flip the screen a little bit because I'm going to bring something back from last week. Last week, click. There we go. Last week, we dealt with this equation. Last week, we saw this equation multiple times throughout the notes that we were taking, and it was fantastic. This equation was y equals x squared plus x minus 6. This is a parabola. It has a U shape. It's opening up. But if we were to quote unquote solve it, if we were to solve, then the answers that we would be looking for would be these 2 points right here. Those 2 points that I just highlighted. Now, in the video that you watched, they talked about it a little bit, but I'm going to go into a little bit more detail. Those 2 points, those 2 pink points that I just put on the graph, they go by many names. One of them is x-intercept, finding an x-intercept. They're also called the roots of the quadratic. They are also called the solutions of the quadratic. And they are also called the zeros of the quadratic. What I'm going to do next is this. I'm going to give you a little bit of a crash course in terms of the definitions, in terms of what it is that we're actually solving. I'm going to remind you of the Tucker method, what I introduced to you last week in terms of factoring. I'm going to show you how all of these things are absolutely interconnected. This function that I left up here, perhaps we will try to solve for that later, but it's a big we'll see situation. So what I'm going to need from all of you, and for all of you at home as well, I'm going to need those notebooks out and open. Haha. Try to change this just a little tad. That's the best I could do with that screen. Notebooks, notebooks, notebooks. Yes, people are bringing back the notebooks that I gave them. Excellent. Bring back those notebooks that I gave you. Yes. Absolutely, yes. Take whatever you need. Get rid of that. Bring that up. There we go. Chapow. Chapow, chapow. Here we go. Today is the 21st. You know what today is? Monday the 21st. You know what today is, though, really? Come on, one of you knows. What's so special about September 21st? What? The song? Oh, I have no clue. Today is the last day of summer. That was a bad word. But yeah, today is officially the last day of summer. Tomorrow's the first day of fall. My wife loves fall too. Do you know why? I asked her one day. I'm like, why do you love fall so much? She's like, because everything starts dying. I'm like, what? And she's like, think about it. Like the trees change color, right? The trees change color because the leaves are dying. Anyway, back to this. Solving quadratics by factoring. Solving quadratics by factoring. Here's what we do. The general idea of factoring allows you to break something up into 2 parts, to break something up into 2 terms that are being multiplied together. For example, if I were to factor x squared plus x minus 6, we did this last week, just to kind of walk you through it a little bit, and I'll remind you with other examples as well. We would take a times c, which would be 1 times -6 to get -6. It's always good to write it down again, even if you're like, I've seen this like 14 times, Mr. Markey. I know, but it's always good to write it down again. Finding 2 magic numbers. Do you guys remember what the magic numbers were for this particular example? 2 magic numbers that multiply to -6 and add up to the b value. What's the b value here is 1. Two numbers. Just give me any 2 numbers that multiply to -6. -3 and 2. They multiply to -6. But what do -3 and 2 add up to? -1, though. I don't need -1. I need +1. So instead of -3 and 2, -2 and 3. They add up to +1. Again, we have to remind ourselves of the Tucker method. That quizzes that you guys are taking online for me that is due tomorrow. I assigned it last Friday, but that quizzes that is due tomorrow at 2 o'clock is all about factoring. You're going to spend your time, your enrichment time, knocking that thing out. If you need to look over the notes on factoring, if you need to watch that lesson again, please, by all means, do that before you do it. You have 3 attempts. 3 attempts to get the best grade that you can on that quizzes. I take those 2, I throw them into a T-chart. It's a 1x and a 1x. There's nothing that I can simplify, and I get something like this. Now, these 2 terms are not the solutions. These 2 terms are not what we call the zeros or the x-intercepts or anything along those lines. These are the factors, not the solutions. And please make a note of that. Please make a note of that. These are the factors, they are not the solutions. And I put solutions in quotes because when I'm talking about the solution to a quadratic, I am talking about something very, very specific. If I just ask you to factor, yes, then we're done. If I just ask you to factor, yes, this is the answer. But if the problem is asking for you to solve the quadratic, now we're going a bit deeper. Now we have to go a bit deeper. Let me show you what I mean. To solve a quadratic means to find the x-intercepts. If I could spell intercepts today. To find the x-intercepts, also known as the roots, also known as the solutions, also known as the zeros. All 4 of these things, they mean the same thing. They all mean the same thing. When you are trying to solve a quadratic, if you can identify through whatever mathematical means you have the x-intercepts of the graph, or what they call the zeros of the function, the solutions, if you could solve for x, if you could get x by itself, that is what all of these things mean. Sometimes you might be faced with that. Sometimes you might be given a problem that says, hey, find the roots of the quadratic, or solve the quadratic, or identify the x-intercepts of the quadratic. They all mean the same thing, which means you don't have to learn like 5 different methods. You could just learn the one method, or the 2 methods actually that I'm eventually going to teach you. There are actually 2 total methods that I'm going to teach you in solving quadratics. We're going to be focusing on the factoring one, the one that we started last week. So, what that means is this. The example, and I am going to go back to this, is y equals x squared plus x minus 6. Mr. Markey, you've shown us this example 14 different times. I know, but there's a reason. There is a reason. You have to trust my madness. If I am told that I have to solve, to solve means set the quadratic to y equals 0. Set the quadratic to y equals 0. There's a reason why that happens. There is a reason why that happens. I want to draw that out right here, actually. Which one's the x-axis? Which one's the x-axis? This is what you can give me. Exactly. Thank you. That's what I was going to say. Just give me a hand motion. Exactly. This is your x-axis, which makes this your y-axis. Okay. If I'm saying, hey, solving a quadratic means to find the x-intercept. I want to find the x-intercept, or the point that crosses the x-axis. I need to find the x-intercept, the point that crosses the x-axis. This ordered pair right here, this ordered pair is whatever the x-intercept is, comma, what's my y value? Ordered pairs, if I'm sitting on top of the x-axis, what's my y value? People just staring straight ahead. Mr. Markey, please don't call on me. Please don't look at me. If I avoid eye contact, he'll never even know I'm here. It's 0. That's the point, though. Look. The y value is 0. The y value is 0. If you're finding an x-intercept, it means that your y value is 0. That's why to solve a quadratic means to set the y equal to 0. And if we do that, ladies and gentlemen, now we are on a roller coaster of a ride right now. Mr. Markey, how in the world are you this alert at like 10-something in the morning? I don't know. How do I survive on 3 hours of sleep with 2 kids and minimal coffee? It's a secret. 0 equals x squared plus x minus 6. Now, here's the logic behind it. We can factor. We already factored. We factored before. I'm just going to show you that right here. When we factored, we got these 2 terms. When we factored, we got those 2 terms. We factored it. So far, this is like the second or third time. No, like the third time or fourth time we've done this. We did this example last week. It was the first example I showed you. We did this example a second time last week. It was one of the last examples of the day that I showed you. I showed you this example when we started the notes. It was the third time that I've shown you. This is the fourth time that I've shown you that this quadratic factors into these 2 terms. And now I have a question for you. It's like a question that goes back to like elementary school. This is an elementary school question, what I'm about to ask you. Get ready, get ready, get ready. What happens when you multiply 2 things together and the result is 0? What happens, or what can you say if I multiply these 2 random things together and the result is 0? What can you say about any of the things? Yeah? No? Oh, yeah. One more time. One of them has to be 0. If I say, hey, A times B is equal to 0, one of them has to be 0. If I say apple times orange is equal to 0, one of them has to be 0. Could they both be 0? Yeah, they could both be 0. But definitely, one of them has to be 0. Now let me bring you to this right here. Look at this, 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 look at this. I'm multiplying 2 things together. And the result is 0. Translation. One of these 2 things have to be 0. This is the logic that I'm trying to lay out for you. You want to find an x-intercept? Set your y equal to 0. Because every x-intercept has a y value of 0. Okay, so I did that. Oh, we factored. Factored! If you can factor, then you can use the next step. If you can factor, then you can solve the quadratic in the following way. Side note! When I literally say side note, I might not be putting it to the side. I just will literally write the word side note. Which means you write that down as well. In terms of this side note, if A times B is equal to 0, then either A equals 0 or B equals 0. This is known as the zero product property. It is one of the silliest things to think about. You're like, yeah, of course, if you multiply anything by 0, you get 0. Yeah, I know you do. You multiply anything by 0, you get 0. What more fundamental thing do you need to know? But this plays a major role. Hey, fun fact, what happens when you divide by 0? What happens when you divide by 0? Did you know that every time you try to divide by 0, a little portion of the universe explodes? Did you know that? No? All right, cool. Everyone's like, Mr. Markey, just shut up and teach your lesson. And I'm like, no, I will do whatever the heck I want to do. All this stuff is made up anyway. You're going to find out like next year, but every single piece of math that I ever teach you is completely and utterly made up. Would you know the difference? Anyway, cool. So if A times B is equal to 0, either A is 0 or B is 0, which means for us, either x minus 2 equals 0 or x plus 3 equals 0. Because of the zero product property, I am allowed to do something like that. I'm allowed to take each term that I factored and set them individually equal to 0. And now I am able to solve. To solve means to get x by itself. Simply going to add 2 to each side. I'm simply going to subtract 3 from each side, and I get 2 solutions. These are my solutions. These are my roots. These are my x-intercepts. These are my zeros. They all mean the same thing. If I were to take a 2 and plug it into my original quadratic, and I'm going to show you that in a moment. If I were to take a 2 and plug it into my original quadratic up top right here, let's see what happens. If I were to take a 2 and put it in right there, and a 2 right there, that's a weird 2. There's a 2. If I were to do that, 2 squared is 4. 4 plus 2 is 6. 6 minus 6 is 0. All right. Let me try it again with a negative 3. Negative 3 squared is 9. 9 plus negative 3 is 6. 6 minus 6 is 0. Visually, you can see where the x-intercepts are on that Desmos program. Visually, you can see this. You can see a positive 2 and a negative 3 as the x-intercepts to the graph. It's not always visual, but this time it is. You can solve by plugging these numbers in and proving that they result in a 0, as I showed you before. Or, and this is going to be the main thing that we're going to be focusing on, you can factor. And once you factor, you can solve. It's very dramatic. I love it so very much. Let's try another one. Let's kind of step ahead with this and let me walk you through what you're going to do. Because in a little bit, I'm going to give you a few examples to try on your own. Let's see here. I don't like that. I'm going to make my own one up. Example. Let's try a 2x squared plus x minus 6 equals 0. And I tell you to solve. This is the quadratic that I have. Zoom in a little bit more. There we go. Now, I can actually type this one in. Let's see. I'm going to type it into Desmos. 2x squared plus x minus 6. There it is. Cool. There's the quadratic right there. Oh, look at this. This is the quadratic that I just gave you, 2x squared plus x minus 6. This is what it looks like visually. That looks like a whole number. Oh, crap, that doesn't look like a whole number. You can probably guess what number that is. You totally guess what number it is, but that's not the point. Guessing is not going to work here. I need to see work. I need to see the mathematical argument. I need to see that you did what you needed to do in order to get this answer done correctly. So, in order to do that, we need to walk through factoring. All right, Tucker method. The Tucker method of factoring. Somebody remind me, what is step number 1? Greatest common factor. Greatest common factor. Now, in this case, oh, look, Mr. Ricky, a 2 and a 6. A 2 and a 6. Yay! What's the middle term? Yeah. The middle term is a 1. They all have to have the same thing in common. They all have to have the same thing in common, whether it be a number or a variable. Technically, the greatest common factor here is a 1. Skip it. Move on to step 2. Step 2 is A times C. In this case, A times C would get you negative 12. A times C would get you negative 12 here. I'm just double checking the chat. I had checked the chat a little while ago, but I realized that the only comment in there was the one that I put in myself. Anyway, I need 2 magic numbers. 2 magic numbers that multiply to negative 12 and at the exact same time add up to positive 1. There's like, what, 1 and 12, 2 and 6, 3 and 4 hike. But one of them's got to be negative. I know you got my answer. I know you do. I'm just trying to give them an opportunity to kind of just sit there and panic for a few extra seconds while they're waiting for me to not pick on them. All right, go ahead. Yes. Negative 3 and 4. Absolutely yes. Now, the T-chart is critical here. The T-chart is critical. The T-chart will get us the correct factors. Those are not my answers. Those numbers are not my solutions. They're my magic numbers. They are my magic numbers, but they are not the answers to this problem. Please keep that in mind. T-chart, negative 3 and positive 4. Now, typically, we'd always do like an x and an x, but we got a 2x squared here. And as we learned last week, 2x and 2x. Mind you, I'm teaching you something new and reviewing what we did last week all at the same time. Whatever. I have to simplify because technically you're going to treat this like a fraction. This is 2 over 4, which reduces to 1 over 2. The other fraction does not simplify. So I end up with the terms 2x minus 3 times 1x plus 2. Now, again, I want to reiterate something very important here. As I wrote on the previous example, this is not my answer. These are not my solutions. These are the factors. When you use the Tucker method of factoring, you end up with 2 factors for the most part, unless it's not factorable, or you have like a GCF. But still, you end up with these 2 factors. When you factor, you end up with the 2 terms that if I multiplied them back together, they would give me the original quadratic. But that's not what I'm here for. What I'm here for is I have to solve. And if you notice, at the very beginning of this problem, this quadratic was equal to 0. Hey, if you turn your head like this, does the equal 0 look like an emoji? All right, anyway. You can set those two terms equal to 0. Now you'll never be able to unsee it, by the way. You'll just be like, okay. But they're equal to 0. And now, because I have two terms being multiplied together that equal 0, now that I have them in factored form, now that I have broken them apart using the Tucker method, the Tucker method's over. I have completed the Tucker method. The Tucker method got me my factors. But now, because of the 0 product property, I can do this. Because of the 0 product property, because of the fact that I have two things being multiplied together resulting in 0, either the first term is equal to 0 or the second term is equal to 0. In this case, I'm interested in both. I am interested in both. And I have to solve them. I don't know what grade you first learned how to do this. Is this like pre-algebra stuff? I really don't know. I've never taught middle school. I don't know. This is like pre-algebra stuff. Maybe. 6th grade math stuff. Solving 2x minus 3 equals 0. For those of you who don't remember, the entire goal is to peel off the outside layers until you get x by itself. You would add 3 to both sides. If you need to write it out, but you can add 3 to both sides and then divide by 2. If you divide by 2, 3 divided by 2 will get you 1.5. Keep in mind, I'm expecting you to know how to do that last part. And then here it's just, subtract 2. And you end up with 2 solutions. You end up with 2 x-intercepts. You end up with 2 what they call zeros of the function. They call them the zeros of the function because the y value is equal to 0. That is what this thing does. That is its purpose. That is its essence of existing. So you can solve the quadratic and figure out precisely when this thing is supposed to hit 0. I think we're ready for a very brief word problem. I said word problem, and several of you just had this PTSD moment. Oh, why, Mr. Markey? Why must mathematics exist? Because it does, and it's beautiful. Why paint a picture? I don't know. I never liked art. Let's do a basic word problem. I have a rectangle. I have a rectangle whose one side measures x feet and the other side, I want to make sure I get this right. That should work. Yeah. Measures x plus 6, which means it's 6 feet longer. Feet. Yes. Yes. Excellent. Altogether, the area is 8. No, not 8. I got to make sure I got these numbers right here. Hold on 2 seconds. I got to make sure my numbers work out precisely. I'm trying to do them into my head while I'm talking to you. Yes. The area is 16 feet squared. The area is 16 feet squared. So the question becomes, what is the value of x? I guarantee you, you could stare at this problem and figure it out in your head within 15 seconds or less. I guarantee you. You could figure out, oh, x has to be this. Yes, x has to be whatever the number is that you said it was. Anybody have a number? Yeah? It's got to be. It's got to be. It has to be 2. The answer has to be 2. Look, 2 plus 6 is 8. So this is 8 feet, and then this is 2 feet. 8 times 2 is 16 feet squared. Yay! Yes. But what if the numbers were a lot more complicated? What if the numbers were decimals? Unfortunately, you get to that, and it's like, oh no, I can't figure that stuff out in my head. Now, this one you could totally figure out in your head. But if the numbers were more complicated than this, you would not be able to. So we have to model a problem here. How do you determine the area of a rectangle? Geometry. How do you determine the area of a rectangle? Length times width. It's just, yeah, length times width. So let's do that. Length times width is equal to the area of the rectangle. Here's the problem that we are faced with. We have to solve for x using things that we have been doing in class. So I'm going to have to do several things all at once. I'm eventually going to get a quadratic. I don't see the quadratic right now, but I'm going to have to simplify some junk down, which means, ladies and gentlemen, a thing that you've been doing since middle school and maybe sooner. What is this called? What is this called? What I just did, what these little arrows mean. This is how everyone is on a Monday morning. This is how I am on a Monday morning. This is how you guys are on a Monday morning. That's the noise I make. What is that? It starts with a D, ends with an distribution. Still, not even after that? Thank you. Thank you. Thank you for laughing the first time I said it, though. It's like, sometimes people don't know them. Anyway, whatever. Distribution. This is going to get you an x squared plus a 16x. I'm sorry, 16x plus a 6x equals 16. Sorry, I was looking ahead to writing the 16. X times x will get you x squared. X times 6 will get you 6x. And that 16 is on the other side. Now here's the billion-dollar question. I would love to continue with the Tucker method of factoring. I would love to continue with what we did with the previous problem. I would love to continue using the mathematics that we have been using. However, there's one thing that is wrong with this problem. There is one key feature that is wrong with the way that this problem looks. Now, we have not made a mistake. We have not made a mistake. But there is something wrong with this. And I need to correct what looks wrong with it before I can continue. Something I haven't really mentioned much. Ooh. What's the difference between this equation and the other examples we've done today? There's one key difference between this problem and the other problems that we have done today. Does anyone see it? Does anyone see it? Do you have an idea? Do you have an idea? It's not obvious. It's not obvious, but there's a key difference here. Let me show you what I mean. The first problem that we did was this. The second problem that we did was this. The third problem that we're working on is this. What's the key difference between them all? Do you know? It could be anything in the middle. That is different, but that's not what I'm looking at. What are the first two problems equal to? What are these two problems equal to over here? What's literally on the right side of the equation? 0. Now this is key. This is key. This is key to understanding this whole thing. You need the equation to equal 0. In order to move forward, in order to proceed with our process, in order to have any hope of solving these correctly, you need one side of the equation equal to 0. That is the only way that we are going to be able to utilize the zero product property. A times B is equal to 0. Well, if A times B is equal to 0, then either A is equal to 0 or B is equal to 0. But I can't do that if it's not equal to 0, which means move this up a little bit. I need to do this. You have to get one side equal to 0. You have to get one side equal to 0. If you do not, then you are going to be lost on these problems. They have to be equal to 0 to utilize the zero product property. Now, I'm not going to go through all of the Tucker method right now, but what I am going to say with the Tucker method is that you do something like this. And those are the two factors that you should be getting. Think about it. 8 times -2. 8 plus -2. They work. 8 times -2, 8 plus -2. They work. I'm skipping past the Tucker method in order to get to the solution that I need. The solution that I need, well, x plus 8 is equal to 0. X minus 2 is equal to 0. Because the zero product property. Now that I have two things being multiplied to 0, one of them has got to be 0, which results in a -8 and a +2. Ooh, don't miss it, 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 don't miss it. I haven't circled my answers yet. I have not circled my answers yet, and there's a reason why I have not circled my answers yet. I've seen several of you did circle your answers already. Don't. There's a reason. There's a reason. There's always a reason. Why have I not circled my answers yet? Well, a couple reasons. Number one, ladies and gentlemen, this is a word problem. This is a word problem, which means a word problem deserves units on the answer. There has to be a unit on the answer, and in this case, the unit is going to be measured in feet. But it's way more important than that. Ladies and gentlemen, it's way more important than that. Let's go back to the original problem. Let me zoom out just a little bit. Zoom out, zoom out, zoom out. Bring this down. Bring this down. Ladies and gentlemen, we got two answers. We got an answer of a +2. We got an answer of a -8. Why am I making such a big deal about not having circled my answers yet? Why am I making a big deal about what the answers are compared to the original problem? We got an answer of +2 and -8. Why does one of those answers needs to be crossed out? Why is one of those answers disqualified? One of those answers is not an answer. It is not legal for it to be an answer. What was one of the answers we got? Yeah. Why? Well, we got -8 and +2. -8 would work in the equation. -8 would work in the equation. But why doesn't -8 work for this? But it does, though. If you plugged it in, what's -8 times -2? +16. But think about this logically. Take a step back from math. Think about real life. This length could be 2 feet. Could this length be -8 feet? No, that doesn't make any sense. That doesn't make any sense. The context of the situation, x can't be negative in the context of this situation. That doesn't make any sense. You can't have a negative length here, which means for this word problem, that is our only solution. Ms. Reagan, then what do we do with this? You ignore it because it's a word problem, and sometimes the word problem doesn't have 2 answers. Sometimes the word problem only has 1 answer based on the context of the situation that you are faced with. I want to give you a few problems. Actually, we'll do 2 specific problems to start with. And they'll be phenomenal. Let's see. I like that one. Yeah, let's do that one. Problem number 1. I'm going to split my paper. Problem number 1. X squared equals 2x plus 99. And the second problem that you're going to solve, I have a 2x squared minus 8x minus 90 equals 0. Zoom in. Now, I caution you. I gave you these 2 problems. Fantastic. For the first problem on the left, you need to get one side equal to 0. You need one side equal to 0. I am going to suggest that you take these 2 terms and you put them on the left side. You move them over. You have to move them over by proper addition subtraction. There has to be a logical reason why you move them over. The 2x and the 99, their signs are going to change. Then, on this second problem right here, please do not forget step number 1. Step number 1 is important. Step number 1 of the Tucker method is greatest common factor. I want you to take the next maybe a little less than 5 minutes, a little bit less than 5 minutes, and I want you to knock out these 2 problems. Go for it. I'm not going over the problems just yet, but again, just a reminder, the best way to learn mathematics isn't hoping that one day it will just absorb into my head. The best way to learn mathematics is by attempting and possibly failing. Not saying failing the class, talking about failing the problem. If you attempt the problem and fail at getting the answer, that is perfectly okay. Because by attempting it and then being corrected on it, that is much better than just staring at it and hoping that it will make sense one day. You got to get your hands dirty, ladies and gentlemen. You got to get your hands dirty. Ms. Murky, I don't know where to start. Start with whatever you think. Compare it to the previous problems that we've done. Compare it to the work that I've gone over with you so far. The method that I've shown you is solid, and it will work with proper practice. You got to trust the method. When I was a kid, we had these, my parents had a stove that, you know how like stoves nowadays, you got to like turn the thing on, it goes click, 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 and then it goes on? You know what I'm talking about? Cool, some people do. Thank you. Well, we didn't have that kind of stove when I was a kid. We had a stove that had a pilot light on it. It was on the top of the stove, there was a little hole. It was covered in silver. It wasn't silver, it was like steel, whatever. And you could see a blue flame in the hole. And basically, when you went on to turn on the stove, it didn't have to go click, click, click. There was always a pilot light on, and that pilot light would always light the burner, which was great. Well, when I was like 4 or 5 years old, I climbed up on the counter and I looked over at the stove and I saw the hole with the blue flame on it. And I thought to myself, I've never seen blue fire before. I wonder what it feels like. So I took my thumb and I put it over the hole. Now, what do you think happened? What do you think happened? Say again? I burnt my finger. I burnt my thumb. I burnt it. I believe that there are a lot of students today that are unwilling to allow themselves to get burnt. And when I say get burnt, I mean be wrong. There are a lot of students today that don't want to be wrong. They don't want to be seen as wrong. They don't want to see themselves as being wrong. Oh, I got it wrong. Oh, I'm worthless. Oh, I'm this. Oh, I'm that. Here's the thing. If you're a grown-up and you stick your thumb in fire and burn your thumb, if you're a grown-up, you know what you are? You're dumb. I'm just saying, it's fire. Come on, you're a grown-up. But if I'm 4 or 5 years old and I'm just learning, and I'm just taking my first steps into education, you have to be willing to make mistakes. You have to be willing to make mistakes. If you're unwilling to make a mistake, then I don't know if you'll ever learn that fire is hot. I know fire is hot. Why? Because somebody told you? Come on, you got to experience it. I'm not saying go start a fire. Don't do that. That'd be bad. Although if you do, let me know. Anyway, for the first problem here, I did see several of you do this. Saw several of you do this where you need to get one side of the equation equal to 0. You do that by subtracting the 2x and subtracting the 99. Now, it is entirely possible that you'll have a negative for an a value. If you ever have a negative for an a value, I'm going to have you take that out as a greatest common factor. I'm going to have you take that out as a greatest common factor. I don't want negatives for my a value. We'll go into more detail another time. A times c is negative 99. My two magic numbers? It's like 11 and 9. But the 11 has to be negative. 11 times 9 gives me 99, but one of them has to be negative. The 11 has to be negative because they got to add up to that negative 2. T-chart, nothing simplifies. You end up with the following two terms equal to 0, and you end up with two answers. I'm going to skip a step here, but you end up with two answers, 11 and negative 9. It's not a word problem. And since it's not a word problem, both answers immediately work. Both answers work. If it were a word problem, then I'd have to think about the context. But I'd get a positive 11 and a negative 9 for that answer. Second problem. What did you notice about all three terms here? They have an Egyptian king in common. Did you see that? They have an Egyptian king in common. They have a 2 in common. Nobody gets me. 2 in common. This joke went over everyone's head. King Tut's real name was Tutankhamun. Y'all are lame. Anyway, thank you for saying they have a 2 there. I can divide the 2 out. Man, I enjoy my job. And I get something like this. Here's the beauty of the whole thing. That 2 that you just took out will not play a role. That 2 that you just took out, technically I can ignore it. But let me just continue and see what happens. I'm going to skip a little bit of the Tucker method for the sake of time. If you did the Tucker method correctly, you should have ended up with these two as your terms, x minus 9 and x plus 5. The x minus 9 produces an answer of 9. The x plus 5 produces an answer of negative 5. Here's the thing. This 2, you can't set it equal to 0 because if you did, it would just be 2 equals 0, which makes no sense. 2 doesn't equal 0, so that doesn't count as one of my answers. Yes, 2 is a factor. These are my factors. She called the 2. You called it a greatest common factor, but it is not one of my solutions. 9 and negative 5 are. Ladies and gentlemen, I'm going to remind you that you have a quizzes due tomorrow at 2 o'clock. Make sure you are jumping on top of that. You have 3 attempts to get the best score possible. I will be assigning something before the end of this week. I have messaged those who haven't taken the benchmark. Please make sure you've taken the benchmark if you haven't already. I need that information. And then we'll see where this goes, because I will be assigning a project next week. And I'm so excited. Anyway, the bell's going to ring in approximately 2 to 3 seconds. I'm going to sign off.